Ya. Buenos días a todos los que están conectados a esta charla. Primero que nada, recordar que este es un proyecto de vinculación internacional auspiciado por ANID, donde la Universidad de O'Higgins es la universidad principal y junto a ella existen otras universidades, tanto chilenas como extranjeras, que son parte del proyecto, ¿ya? El proyecto se llama FOBI 210023, cuyo título es Microredes eléctricas para una agricultura energéticamente sustentable, ¿ya? Y hoy día tenemos un invitado de Dinamarca y ahora vamos a cambiar a inglés para introducirlo, ¿ok? So, hello everyone, thank you for attending to this today's presentation. For me, it's a pleasure to have today to Dr. Navid Bayati, who received the master degree in electrical engineering from Amir Kabir University of Technology, Tehran, Iran in 2017, and the PhD degree in electrical engineering from Aalborg University, Aalborg, Denmark in 2020. In 2021, he was a postdoctoral researcher with the University of Southern Denmark, Odense, Denmark, where since 2022, he has been an assistant professor on power system protections. His research interests include power system protection, DC microgrids, and fault detection. And also he was the recipient of the top 1% reviewer in the world in 2019, okay? So Dr. Navid Bayati today is going to present the talk entitled AC and DC microgrids. Please, Navid, go for it.
Yes, thank you everyone for having me. So today we want to talk about a general topic of the AC/DC microgrids with a little focus on the protection, because I focused a lot in last maybe 10 years on the protection of the different systems. So it's my biography. Claudio told that, so we can go ahead on the introduction about the University of Southern Denmark, or SDU. In SDU, we have different campuses. We have 6 different campuses around the Denmark, and we are now located in Sundabo. And also, we have some colleagues in Odense. We are in Sundabo, and we working on the Center for Industrial Electronics, or CIE, in Sundabo, and we focusing on different aspects of electronic devices or energy systems, and we have different groups here. We have control and protection of the smart grids, we have the passive components, power converter systems reliability, and other different groups. But here we are in the control and protection of the smart grids, and we have very small groups here and working on different kind of the smart grids. Or we talking about the smart grids is more the same as a macro grid. And here we're focusing more on the renewable energy systems, PV systems, wind turbines, and battery energy sources together to provide more flexibility to the current power grid. So we have the power grid right now, and if we can localize some production by the renewables, we can go on the green transition more fast, and also we can eliminate the massive production by the power plants. So here we have a lab, and more or less we have a microgrid here. So we have AC grid simulator, we have DC sources, and we have some converters. So together now we have AC/DC microgrid right now that controlled by the help of the DSpace, and also we have the opolarity, and by opolarity we can have some real-time simulations. So if we have, for example, microgrid, we can work on the opolarity, and we can connect it to some real world components, and then we can control and protect anything that we want. So this is a structure of the system that we have. So we have some hardware in the loop, and I don't want to talk a lot about the hardware in the loops right now, but just have a glance view of this hardware in the loop. So we have some hardwares, and for sure we cannot have all hardwares together. For example, we cannot have the wind turbine, big wind turbine, and have some control methods or protection method on that wind turbine. So we can simulate that wind turbine in the Opalarity, and then we can connect them to some real world components. For example, a hybrid ESS here in the left side. So we can focus on the impact of the energy storage systems to the wind turbine by this setup. And here we have more or less another microgrid that's working. We have the grid simulator, so it's simulated grid. We have some loads, DC sources, and battery simulator together, and we make the PQ or power quality scale. Okay, let's go on the topic of the microgrids. So when we talk about the microgrids, as you can find from the name, is a grid, but in macro side. So when we have a utility grid, the whole of the productions, all of the components, transmission lines, all of the loads, and everything is connected together and shape the power system of the country or utility. But when we talk about microgrid, it's a grid, but in very small size. So in the microgrid, we should have some production of the power, and also we will have some consumption of that power. Just assume a neighborhood, and the neighborhood is, as you can from the picture. So we have some renewable energy. The renewable energy is depend on the location that we talk about. So if we talk about some microgrid in North Pole, for sure we cannot rely more on the PV, and we can more rely on the wind. And we can assign some renewable energy resources. It can be on the farm side. For example, we can have 1 megawatt or 2 megawatt PV farm, or we can have some rooftop PVs. And then we have the heat and power. In Denmark, we have district heatings. So if we have, for example, some electrolyzer or power to X components, we can connect the heating or thermal losses of that one to the district heating that we currently doing, and sell the residual heat to the district heating and for homes. So here we can also have some EVs for sure. In the next years, everywhere we will have some EVs, and also we can have some local generators, for example, diesel. But because we propose the microgrid to remove the pollutions, it's better to move on the renewable side. And also we have some homes. So if we disconnect this microgrid from the main grid, because we have the production and the consumption compact together in one side, for sure we can consume the power to the homes without any disruptions. So it's a benefit of the microgrid. Without connection to the grid, we can do that. Normally, we have this connection to the grid because we need high reliability. And if we have some exceeds per production, we can store for sure in the energy storage. But if we have higher production, we can sell to the grid, or we don't have too much power production. For example, during the night, if we have some microgrid rely on the PV, we can consume some power from grid. So it's better to connect always to the grid. But if we have some problems in the grid, if we have a lot of microgrids around the country, for sure we can keep the power inside of the microgrids. So in a microgrid, we can have different type of sources: wind turbines, fuel cells, micro turbines, and PVs. And because the nature of majority of loads is DC, for example, the television, if we talk about the loads in the cities, for example, television or the data centers or PC or everything is DC, and inside of them we have some converters. So if we remove this kind of the conversion from the AC to DC, and we have the grid, we have the microgrid that completely working on the DC, obviously we can remove the converters. Removing the converters for sure can have less investment. Then we can have less, for example, the power losses because we don't have the converters. And for sure, if you focus on the wind turbine, for example, in the wind turbine, if you want to connect a wind turbine to the grid, to AC grid, as an example, first we should convert the wind turbine to AC-DC converter and then DC-AC converter. So if you have a microgrid that's working completely by DC process, for example, then we can remove the last AC-DC wind turbine and only we can work by AC-DC. So then we'll have fewer power losses and costs compared to the AC microgrids. So if we have the microgrids, we will have some advantages. Just a glance. So the efficiency is higher. Why is higher? Because if we have some generation that is close to the loads, assume that you have apartment, you have a company, or you have a factory or anything, and you have inside of the factory, you have some PVs that can produce the power that you need inside of the factory. So for sure, here we don't have anything regarding to the losses of the transmission line from the production to the load side. So it's more efficient and low cost, and it's obviously clean if we focus on the renewables. So if we have a lot of microgrids in the power system, it can improve the operation and stability of the power system. Why? Because for sure, every microgrid can produce the power and consume the power and only need the power from the grid if they cannot produce enough power. So for sure, if we have a lot of microgrid in the country, then the stability of the system is higher. So if you have, for example, a short circuit in somewhere, if we have the short circuit inside of the microgrid easily can be disconnected from the grid. So we will not have any short circuit from the grid side. And also, if we have the short circuit in the grid, we can operate all of the microgrids separately without having the grid. So the stability and reliability is super high. And we can have some grid services by the microgrid. For example, if we have some additional power production, we can sell to the grid. If the grid just went to the blackout, for example, we can start to some restoration from microgrid side. Or for example, if we have some voltage drop in the power grid, the microgrids can also provide some services to that one. So in the microgrid, we can have many different advantages and services to the grid. So this is a structure of one AC microgrid. So here we have the utility grid that we have the PCC or point of common coupling, and that one is connected to the switch. And this switch can change the microgrid from islanded operation to grid connected operation. So we have two kind of operation from any kind of microgrids: islanded mode, and islanded mode is just as an island, is not connected to anywhere. And grid connected mode, that is connected to the grid. And then if we have some PV panels, as you can see here, the PV panels are connected to the DC-AC converters. Together, it can be different modules. And we have some distributed loads. We have the wind turbine, and as you can see, the wind turbine connected to AC-DC and DC-AC converter. Why we need two converters for the wind turbine? Because the wind speed is can change by the time, and for sure, if we have different value of the wind speed inside of the wind turbine, we have some generators. If we have different speeds, as you know, we will have different frequency in the output of the voltage or current. So we need always 50 Hertz. So first we should make that one DC and again DC to AC. So you can see that here, if we operate the whole microgrid in the DC microgrid, we can eliminate a lot of converters. Fuel cell also working in the DC, so we can eliminate converter and also some loads. So if we move to the DC microgrids, in the DC microgrids, because the majority of loads are DC, so it's easier to work on the DC. And also, if we have, you know, some larger DC microgrids to some megawatts, as you know, if we work on the DC power, we don't have any skin effect. So if we don't have any skin effect, for sure, when we have skin effect by AC, the resistance of that transmission line will increase. So the higher resistance is higher losses. But in DC cables, we don't have skin effect. So the power losses by the transmission line or any cables in whole system, if you just count the transmission line, the lines in whole of the system, it will be 1,000 or 100 kilometer. So we don't have the skin effect in all of them. So the power losses in the whole system can decrease by 15 to 20% if we move from AC to DC's operation. The safety is higher, and the converters that we need for connection to the sources and the loads are lower. So for sure, we will have lower heats, we will have lower power losses, we will need lower investment. So from the cost point of view and the converter view, for sure, operating the system in the DC is a better way. And because when we talk about the microgrids, always we need a storage system. Why we need a storage system? Because if we have some renewables, we have a lot of uncertainty. So if we have the uncertainty, we should keep the energy that we produce, for example, during the day by the PV, and store that in the storage system and send back to the loads later, for example, during the night. And in the DC systems or DC microgrids, because we don't have any frequency, we don't have any phase, we don't have any problems for making this synchron of different components. As you know, if you have the AC microgrid, AC diesel, AC motor, then if we want to connect them to the main bus, we need some phasor match. So we don't have any phasor, we don't have any frequency, so we don't have any problem regarding to them. So this is a structure for the DC microgrids. When we talk about the DC microgrids, it can be one home as a DC microgrid, or it can be one neighborhood, one city. So here we have a DC microgrid in a very small site. We have a home, for example. Here we have some rooftop DC power that connected to MPPT, and then we have some racks, some UPS, some storage system, and also some converter. The whole of the system working by DC, and then it's connected by a DC-AC converter to the main grid. So it's connected to the main grid, but it doesn't mean that always we need the power. So it's DC microgrid for the data center. As you know, the data centers by the concept, by the nature, should operate it in a DC mode. So if we have an AC microgrid, we needed an AC-DC converter for that one. But here, because we have the DC microgrid, we don't need any converters for connection of the DC data centers. So the PV power going to the data center, and if, for example, during the night, we need the power, the UPS and the battery can make some power flow to the data centers. And also because we have the grid, during the night, we can have some power injection from the grid side to the data centers. So if we have the disconnection from the grid, for sure we can produce some power. We can produce some power to the data center, but for higher reliability, always we should make sure that for the data center we have some connection to the grid. And here you can see that if we move from the AC to the AC microgrid to DC microgrid, we can save around 15% of the operation energy normally. Here we have a AC/DC microgrid. Here we have some in the left side we can see some AC production. It's a hybrid microgrid or AC/DC microgrid. So in the middle you can see DC subgrid or DC. It can be power production. The DC production is normally PVs. So we can make the compact all of the DC production somewhere, all of the AC production somewhere, and we can move the DC loads in close to the DC production and AC loads close to the AC production. So we can still save some conversion here, and we can just send back some exit power production to the grid. So when we talk about the microgrid, AC or DC does not matter. When we talk about the microgrid, any systems that's working by complete electricity and separately without connection to the grid is kind of a microgrid. So assume that the aircraft has some power production, power consumption by loads, by different motors, by control systems, light or anything. So the aircraft is kind of microgrid. So here is a pretty general structure of aircraft that is working on the DC. So the main bus is the DC bus. So we operating normally aircraft by 270 volt. So this is the main bus, and here we can see that the generators producing some AC power. So we can convert that to the DC, and then we have some motors and some loads in different levels, and also the storage system. So we can make all of them compact together and make a microgrid. And normally aircrafts that or all electric aircrafts are a kind of microgrid. So microgrid is not always a system that's located in lands or located in the cities. Here also we can have a shipboard or ship that's working as a microgrid. So we have a lot of electric ferries, electric ships here in Denmark. Obviously, we have some charging station. The charging station are located in the port, and during the one trip, when the ship or ferry just started the trip from the port, we started to charging the batteries of the shipboard or ferry, and then when the ferry started the travel from the port, it only uses the power from the batteries. Here on the right side, you can see very general structure of a shipboard. It's also working on the DC. We have some generators, and then we have some motors, and the buses connected to each other, and also we have some fuel cell and the battery to provide some power balance or power sharing in the system. Also, we can remove the generators, and only we can focus and operate the systems by batteries. In the left side also we can see a diagram by the Typhoon Hill. Here we can see we have some engine generators, we can have some storage systems or battery, and also we can have some motors. Another type of the microgrids is islands. Here, for example, this is an example of the Roma Island. It's not the real one, so it's a simulation more or less based in Denmark. So we have a grid that is connected by AC/DC converter to the islands. So island have some offshore wind turbine that's connected as by AC/DC converter to the system, because the whole microgrid is a DC, so we don't need two converters for the wind turbine. Also, we have some fuel cells in the left side, because also recently the Denmark focused too much on the hydrogen production. We can use that hydrogen for the fuel cell. And then we have some batteries and PV systems in south. So totally this system can work without connection to the grid. So we have the island. If we just miss the connection to the grid, anything happened to the grid, or with any reason, short circuit or anything, then we can easily operate the system without any problems. So in the microgrids, DC or AC, for sure we will have different control and protection components. So every resources, wind turbines, PVs, should have some frequency controller, because if we work in the islanded mode, and we're talking about the AC microgrid, if we work in the islanded mode, for sure the frequency of the system should remain constant. So the frequency should remain in the 50 Hertz. So we have a lot of controllers for all of the system, and we have the island detection and that connected between the grid and the microgrid. And when we have some islanding, then the setting of the control systems in the microgrid will change to the island mode. And one of the largest per production in the microgrid will go to the slack mode, and then we can keep the control or frequency of the system. And also in the voltage, also we have the same one. But in the protection, if we working in the microgrid side, because the microgrids is more on the converter level, we have a lot of renewables, and all renewables connected to the main buses by converters. So when we have these kind of systems, for sure we don't have any inertia. So we don't have any inertia in the system, and when we don't have any inertia, the rock-off or rate of change of the frequency or rate of change of the voltage, the rate of change of the current during the fault or any kind of short circuit or disturbances is high. So if we have a fault in the microgrid, then the fault current going very fast to the peak point. But if we talking about the power system, normally we have around 5 or 6 cycles to remove the faults based on a standard, and somehow if we have huge inertia, we can extend that to the sometimes 10 cycles, so around 200 milliseconds. But in the microgrids, normally right now we don't have too much standards, but in the microgrids, because the rate of the change of the frequency is the change of the current is too much high, then we should detect, locate, and isolate the fault very fast in less than a couple of milliseconds. So any kind of the components for the protection that we have in the power system cannot be directly working in the microgrids. And also when we talk about the DC microgrids, for sure, if we have some protection services, protection relays that working by phase frequency or phase or something like that cannot be useful in the DC microgrids, because normally we don't have the frequency and phases. So we should normally in the microgrids, on DC microgrids, normally we can make our own protection system, and the protection systems are different. They can work in localized, or they can work in by the communication link. If we talking about the working with the communication link, the communication link can increase the costs, delays, noise, failures, and packet dropout. So normally it's better to work for protection systems that's avoiding having the communication link and locals. We have two kind of faults in the any systems, but now we more specify talking about the faults in the microgrids: low impedance faults and high impedance faults. So the high impedance faults are a kind of faults that the value of the resistance of the fault is high. Then the problem is that if the fault resistance is high, for sure we don't have any too much fault current. So it's really hard to detect this kind of fault very fast. And also in DC microgrids, because DC microgrids are some special microgrids, it's really hard to avoid the impact of loads. Normally in power system, we avoid having the impact of load and the protection because loads cannot participate too much in the fault and the protection. But here in the DC microgrids, because we talking about, for example, data centers, their behavior during the fault are different. So we have different challenges of protection of the microgrids. So here we can assume that we have the microgrid here. We have the grid that connected by AC/DC converter to the recloser and connected to this system. So as you can see here, we have load 1, load 2, and load 3, and also PV1 and PV2. They are connected by some DC/DC converter to the main bus. As you know, because we don't have any transformer for the DC application, we should use the DC/DC converter. So we should increase the voltage level by the DC/DC converter, then we can connect them to the main bus. So we have the PV here and load here. The problem is that if, for example, we have a fault in F, in the load 2, then the fault current came from the grid, PV1 and PV2. So we have different fault current that came from different sides of the grid to the faulty point. But if we have one sensor, for example, in the converter number 1, we only can sense the current came from the grid. So we cannot find anything relating to the PV1 and PV2. So normally in this system, we should have sensors everywhere. We should make a SCADA system or some data centers or some DPUs. Then we can connect them together and send the data all together and make some decision. So the direction of fault current is different. Sometimes it's from right to left and left to right because it's not radial, it's more meshed. And also here, when we talk about the converters, they cannot work too much on the high fault current. So if we have a fault in, for example, load 2, the converter number 3 cannot work too much on the huge fault current. So we have some limitation capability by the converter. So they can limit the current when we have this kind of faults. And so when we need the data or sensors from all converters, converter 1, 2, 3, and 4, to find the fault current or current in the system, we need for sure some communication links. And communication link makes some challenges, for example, noise and delays. And right now we don't have too much guides and standards regarding the protection of the DC microgrids, so it's make too much hard to protect these systems. Here also we have, if we talk about some larger power system or some larger microgrids, we can have different zones, and then we can protect each zone separately. So inside of the microgrid, we can also have some nanogrids. So the protection of power systems was relied on the overcurrent protection, impedance-based protection, for example, distance relay, and the communication-based protection, and some new methods, for example, wavelet-based and intelligent methods. So we can also modify them to implement in some larger power system. So if we focus on different methods that can be applied to the microgrids, or especially DC systems, we can have different advantages by them and different disadvantages for them. And you can see that here. We don't have any perfect methods, so we need to more or less modify a method and make or new methods for these systems. So traditional protection systems and traditional relays cannot be applied to DC microgrids. So how is the fault behavior that we talk about, the high Rokoff and the high change of the current in the DC microgrids? You can see here a DC fault in a DC microgrid. As you can see, the fault current going reaching to the maximum value very fast. You can see the slope is more or less infinite. So it's going very fast. But in the AC systems, we have 10 cycles or 200 millisecond time for this one. So it's really hard and harsh to clear the faults on these systems. And when we talk the high impedance faults, the high impedance faults is something like that. We have some oscillation, and because the fault impedance is too high, we have some oscillation. It's something like an arc, and this oscillation, the magnitude is not too much high, and it's really hard to detect them. But if these oscillations remain in the systems, it can make some heating, and sometimes we have some firing in the system. So here is if we want to, if we have here AC microgrid, and if we want to have a protection by the normal overcurrent protection, we can install different relays everywhere, and we can protect the system by this kind of relay as a traditional method. You can see that here we have the grid. It's connected by AC-AC converter, or we can have some transformer. But when we have the AC-AC converter, for the connection to the grid, we can have some switches, disconnection switches, and also the islanded detection inside of the converter. So it's expensive against having some transformer, but it can provide us many different functionality. So also this sensor can be used here, but normally because the lines inside of the microgrids are too small, it's not too much accurate and applicable if we want to install some distance relay inside of the microgrids. So what is the solution for protection of DC microgrids? Having some novel methods. So for example, this is a novel method. We have here a line, and we have some circuit breaker one side, some one with circuit breaker another side, and we have some relays here. So relay just have some sensors or CT connected to sensors. So we apply some mathematical morphology based methods on this one to detect the faults. And here are some real and practical output for this method. So we implemented this method on the lab, and we applied two LIF or low impedance fault and high impedance fault on the transmission line of the DC systems, and we applied the method, and you can see that the fault current going too much very fast and reach to the magnitude, and then we have some disconnection, and then we don't have any connect. So this method was fast, and I think we detected the fault in less than several milliseconds. And you can see here we have some oscillation in the system is because of the noise. Also, we need some coordination inside of the microgrid, but the problem is that when we have the coordination, and what's the meaning of the coordination? To make sure that if you have, for example, fuse for every loads and relay in the main side, if you have some faults inside of the load, for sure fuse should act first. But if we have we move from islanded mode to grid connected mode, the setting between them will change. So we need some adaptive coordination between the fuses and recloses. So here we proposed the method for changing them, for providing some adaptive protection of the fuses. So here we selected the fuses by different settings that are made for DC systems. So normally when we talk about the fuses, the AC equations and AC curve and fuse equations are made for AC systems, but here we changed that for the DC system. We saw that the behavior of the fuses on the AC and DC systems are different, so we can have new or different coordination for the fuses. Here also you can see that if we want to make some coordination between the fuse and recloser, we can put the fuse curve between the recloser curves. It's also the same. If we apply the method on this simulation and DC microgrid, and we saw that this coordination can save fuses, and you can see the data collection and the different behaviors of the fuses here. So for the load side, we have also some challenges. If we have the constant power loads or data centers, the behavior behind of the data centers or constant power load is that the power should always be constant. So if we have the fault, the current will drop, because for sure we have the voltage will drop, because for sure we have the fault. When the voltage will drop, then the current should increase to compensate that drop and make a power constant. So then, as we can see here, the delta V to delta I is a minus value. So during the fault, from the constant power loads, we have a resistance that the value of the resistance is minus or negative. So the protection is different. Here we have a microgrid, and we propose a method to use the sensor from the main bus that's connected to different CPLs. Here we can see that we have the PV system, wind turbine, grid, battery, and motor, all connected to each other. So we use the sensor in the main bus, and we use some equations based on the constant power loads behavior to estimate the location of the fault. So here are the equations, and we use some estimation method to doing that. And the estimation method was least square technique. So when we talk about the microgrids, more or less, if we want to study and research of them, it's very hard to make one microgrid in the lab and start to focus on a study of them in the protection, control, or anything. So we have different methods that we work, we're working on that, or we worked on that. The first one is a simple setup. So simply, if we want to very simply simulate or emulate the microgrid in the lab, we need oscilloscope, we have fault resistance and DC power production. And then if we want to make a line, for sure, we can have some inductances or resistances that connected to each other. Inductance is better because when we talk about the, for example, transmission line, the relation to the X to R is high. We can work on this and see the behavior of the system. But as we can see here, it's not accurate. We cannot apply any method on this. So we should move to some methods that's working with, for example, DS space. In the DS space here, we have some power supplies. We have the DS space, and what is the application of the DS space? DS space is a tool that can connect the sensors and real components to the MATLAB. And then if we have some orders, we can send to the DS space, and from the DS space to some switches. Here we have two power supplies. If we have, just assume that we have a line, two power supplies from two sides. We have some converters here. You can see from the converter, we have some sensors that connected to the converter and then connected from the other side to the DS space, and from the DS space to the PC. We have some SSB here or impulse switches. So if we want to, for sure, we have some pulses that go into these impulse switches, and that makes some PWM for the converter. For if we detect the fault, we can just send the zero signal to the PWM generator, and it will act as a switch. And then we can connect that to some lines, motors, and the fault resistances. Here we produced this result by that DS space setup. Here we have the newer one that we currently working on that, because it's really hard to make the microgrids or this microgrid in a real world, we have the polarity. And what is the application of the polarity? Polarity is a system based on the FPGA. So if we simulate something by Power Factory or MATLAB inside of the PC, we can connect to the polarity, and then we can compile and implement to the polarity, and polarity real-timely can simulate. So if we have a controller, if we have a protection method, we should be able to implement that to the real world. So if we have a lot of complicated equations, then the computation time of that is too much high. So for example, 2 seconds it takes to calculate something, so it's not useful. We should be able to implement that on some real-time systems. So we implement that on the polarity to see that our method can work on real-time or not. Also, we have some outputs and inputs that then we can connect the polarity to some relays, some converters, and some systems in your real world. So we can more or less connect the actual systems by polarity to some methods, some systems inside of the PC. So thank you so much. So if you have any questions and collaboration, this is my email. You can send your inquiry to me. Thank you so much.
Thank you, Navid. Very nice presentation.
Thank you.
Now, if you have some question, please raise your hand. Questions?
Hi.
Alex.
Hi.
Please.
Hi, Professor Navid. Thank you for your kind presentation. It was really nice knowing what you are developing in your university. I have some questions, but these are more general related to the operation of microgrids, not too much related with the protections.
Mm-hmm.
So I would like to know what are the main technologies that are being used for energy storage in Norway? Could you know some?
Currently, we have for the microgrid side, we usually it depends. If we're talking about some loads that's working during the line time, we usually working in the battery because efficiency is high and the investment is not too much. So we use just a battery. But if we, for example, we're working on the aircraft and we want to store some the kinetic energy of that one, we're using some ultra capacitors. But here in Denmark, because the main TS of the Denmark want to install some offshore wind turbine in the west around 10 gigawatts. It's really hard to store that amount of the energy in the battery. More or less is impossible. So we're using here some electrolyzer. So we change that power to hydrogen, and then we can store the hydrogen, and then by some fuel cell, we can convert that again to the power. If we talk about some mega or giga, we're using right now in the power to X. We don't have too much power to X, but we will have.
Yeah, thank you. And also in the operation of a hybrid AC-DC microgrids, you have the interlinking converters to connect the AC side to the DC side. What would be a good objective or how to control the power flow between the microgrids? What is the main criteria that you're using to operate the interlinking converters right now?
So here, it depends on the economical aspects also. If we have more cheap production for sure in the DC side, because in the DC we have lower converters and losses is lower, so it's more preferred to have some power production in the DC side. So if we have some exit value from the DC side, then we can more or less sell to the grid. Then we have some connection to each other, because the DC will operate separately, AC will operate separately. It's more about the controlling of the residual value of the power that we need. So if we cannot provide any power in the AC side, we can have some help from the DC. This is the reason that we have the microgrid clusters right now. We have some microgrid clusters, so we connect the microgrids together and make some power sharing between the microgrids. It's more or less same, and it's more about providing the power balance.
Yeah, thank you. And also, what would be a good option to improve the inertia of the system in isolated operation?
Here we, in Denmark, inertia is going low and low every year because we install a lot of renewables. Right now, there is no very perfect solution if we talk about whole system. But if we talk about the microgrid in very smaller scale, we can have some capacitors that can make some virtual inertia.
Yeah. Thank you. And also in the example of the island, of the microgrid that is implemented on an island, what is the size of that island and the capacity of the microgrid that you are
that one is
considering?
not implemented very well. It's more on simulation, but as I know, the population was not too much, maybe 4,000, 3,000. It's not too much.
4,000 people,
I think.
Yeah. Yeah. Another question that I have is that currently there is a trend of studying cyber attack issues in microgrids. And it's I think that it's quite similar when a cyber attack is present in the microgrid, and it's similar to a fault. So how can you differentiate when it's a cyber attack and when it's a real fault?
Yeah, I don't work too much on the cyber attacks, but in the cyber attacks, when we have the cyber attacks, we have this kind of cyber attack when we have too much communication links. Normally, we don't have too much communication links because we're talking about the smaller scales. I think we don't have too much problems, but for sure, as you can see from the news, every day we can have some cyber attacks, and some of them is successful, unfortunately. But I think it's easily can be separated if we compare the value of the sensors different ways,
Yeah.
or by some blockchains.
Yeah. And the last question is, can the protection algorithms be implemented along with the control algorithms in the same DS space?
In the DS space that I had before in the Alborg, first we had the control methods, and for the converters, so the control methods just try to do the job, and then after that we applied the protection, and the protection is just for detecting of the fault. And because the detection of the fault in the DC microgrids or the DC systems should be very, very fast, in a couple of milliseconds or microseconds, then we can ignore the controls, because the controls needs more time. So we can just do and have some decisions from the protection system.
Yeah, I understand. Yeah, thank you, Professor, once again. And it was really nice hearing from you.
Thank you.
Thank you, Alex. Navid, we have two questions in the chat. The first one is, in your opinion, what should be the role of the system operator about fault detection capabilities in microgrids?
Yep. Normally, because right now, because we're talking about the very small scale microgrids, we have protection of the loads by fuses and the protection of the main resources by some relays. And the relays it can be connected to the converter side, because sensing is also in the converter side. So the fault detection if we talk about the AC microgrids, more or less now is same to the power system, but the inertia is too low. So we try to act as fast as possible, because we don't have too much standards right now. So fast as possible is better.
Okay.
And for the next question, your opinion, what would be the rule of communication network when the microgrids interact with the utility operation? Because the microgrids is more or less the operation are different with the utility grid. Utility grid is a TSO, or if we talk about the DSO, so they are not client of each other. So as I know, in Denmark, we don't have too much sending and receiving of the communication or data between them. So they working completely different, and DSO only have some information about the bus that's connected to the microgrid, if the microgrid is small. But if the microgrid is large enough, the inertia or the power production is sent to the DSOs by real time to have some planning for operation of the system.
Thank you. More questions? If you have question, please raise your hand. Navid, I have a question.
Sure.
As you said, DC microgrids has some advantages when we compare them with AC microgrid.
Yep.
Based on that, I wonder how is the technology or the level of the technology related to DC microgrid. For instance, if I want to implement a DC microgrid at home, can I go to the shop and buy DC plug? There are some standards. What is the current technology related to that?
Yep. It seems that the technology is not developed too much now, and more or less when we talk about the DC microgrids, we talk about the data centers.
Okay.
Because data centers are operated by DC, and you can see the data center, for example, for the Facebook is too much big, is larger than the factory. So it's more developed on that way. So data center, we have some data centers that working as a microgrid, but for homes or apartments, it's not, because the equipments that we have, for example, television, working with the AC. Inside of them in the nature is a DC, but currently they should have some AC plug.
Okay. Okay. So thank you, Navid. Thank you to everyone for attending, and thank you again for that very nice presentation.
Thank you, everyone. Thank you.
Bye-bye. Thank you.
Have a nice day. Bye.
You too. Bye-bye.